Okay, so recording. So as I was saying, and I thought that well, it's a good idea so that everybody can hear, even if you're not here in class. So, folks, the questions that some of the questions that I'm going to put on these tests, again, there are online calculators and some other type of software that would be able to calculate for you an antiderivative, for example, say the antiderivative of x squared plus x minus 1. But the point is, well, you get the correct answer, fine. So you'll get some points there. The point is to also show your work. As you noticed, I'm asking you to show your work. So there's going to be an explicit question at the end where it says, show me your written work. And I want you to make a conscientious effort to show the work that leads to those answers. I don't want just, answers without any work. And in some cases, I commented on your tests, the work that you did here doesn't reflect correctly the answer. So some people did the work, they got some of it correct, some of it not correct. They got an incorrect answer, but somehow out of the blue, they picked the correct answer on the test. So that is, that is a trigger to me that, well, either you just chose the answer by luck, or you certainly don't understand how to get that answer because your work doesn't show that. So so I want you to make a conscientious effort to show me your work, and that's why today's lesson will be focused only on doing practice problems like those that you will see on the test. But again, show the work like we do here in class, so that everybody can can be confident, and that increases your confidence as you move on to calculus 2. Increases your confidence that you can actually do these things on your own. So maybe there you will not be allowed to use a calculator. And then what do you do if you need to calculate various antiderivatives and things like that? So that's a point that I want to make. Now, some of these questions, and you saw one example last time, ask a little bit of trigonometry, as in, some maybe some special values. So this is kind of a level that we have here in Calc 1. Essentially, know the definitions and some small identities, sine and cosine. The basic one will be that one, sine squared plus cosine squared equals 1. And also the relationship between tangent as sine over cosine and secant as 1 over cosine, things like that. So that's the level. And maybe some values, some special values of these trig functions that could be potentially calculated with a calculator. You just have to be a little careful to set your calculators in radians if you use radians, because we use radians mostly in calculus. So with these values, you can essentially calculate any integral, any calculus 1 level integral. But that's going to be a different story when you move on to calculus 2. So that's what I want to make everybody aware that in calculus 2, you will need a lot more trigonometry to be able to calculate those integrals. Those are much more elaborate and require a lot more work. So that's why, going back to where I started, it's very important to know how to do these simpler integrals, the antiderivatives, on your own. And then when you move on to calculus 2, you can apply these techniques and you can build on this. You have a strong foundation here. You can build on this foundation. You look back at what you did in pre-calculus when it comes to trigonometry or so, and then you put these together, and then you build your calculus 2 techniques. So as I said, I am aware that most people here are not even math majors, but we need to teach the class as if everybody were a math major. So I'm gonna insist on you knowing these things because again that's the material and that's the requirements here. So that being said, folks, I'm not going to put extremely challenging questions or anything like that. Everything that I'll put on test will be something very much like the stuff that's discussed here. All right, that being said, let us get to work with these things. So administrative things are always boring. However, math is certainly not boring. So we are going to move on here. And again, remember 4.4, that's the lesson we started last time. And it says indefinite integrals and the net change theorem. So let me write that again. Integrals and the net change theorem. And folks, that says, oops, sorry about that. There we go. That says, I told you that this is really indefinite integrals, folks. Everybody needs to remember that an indefinite integral equals an antiderivative. Very, very important. So an indefinite integral, antiderivative. So just remember, there's nothing new. I told you last time, nothing new, folks, here. The net change theorem is nothing else than the fundamental theorem of calculus. It's just a rewording of that. So this one lesson that we're talking about today, folks, is just a review of the techniques that we learned up to this point. There's nothing really new in this lesson. It's just the terminology. Now, the terminology comes with, so for indefinite integrals, we use this type of notation. We use an integral from indefinite integral. All right, so indefinite integral is an integral. It's an elongated, so the integral sign of f of x dx. When you see this kind of notation, so remember that is just notation, mathematical notation for the antiderivative of the function f of x. All right, so this it's like mechanically, folks, from a mechanical point of view, what you're doing, you're dropping these guys and you're saying antiderivative of f of x. So these two, the integral symbol and the dx, come together for reasons that I told you have to do with the way the definite integral was defined as the area with subdivisions, and the dx is the width of the subdivision and things like that. So you don't really have to remember those at this point in time. Just understand that that really means an antiderivative. So that being said, in your book, there is a table, but this table is nothing new. So if you look at page, and I'm going to say here, page 331, so the table that's given there is just a repeat of the stuff that you already knew. For example, I'm going to write an example here. So it says here, the integral of k dx equals kx plus c. So let's see what that says here, folks, in plain English. In plain English, it says if I have a constant called k, the antiderivative of that constant is simply k times x, and then you add a constant c. So, so the antiderivative of the constant c, k is kx plus another constant c. So forget about this. Even you can forget, because most of the time in calculus 1, you don't need that extra constant. So this is one of the formulas that's given in that table. Another formula that's given in the table is this one here. For instance, so let's do this one. The integral of cosine x dx. And it says here that is sine x plus c. So again, what does this say in plain English, folks? So this notation here simply says that the antiderivative of cosine x is sine x, plus a constant plus c. So basically, we're not learning anything new really here. We're just rewriting the things that we already knew in terms of by using this notation. So these two symbols together. So when you see things like this, integral and dx, and something here, that really means the antiderivative of this question mark. So that is the situation that we're discussing right now. So we're just introducing some notation, folks. Nothing intelligent here, other than we're just reviewing, if you want, antiderivatives in this section. There's a few other questions there. For example, this one, this is important. I've got to start with this one maybe. The antiderivative of x to Vn. So the integral of x to Vn dx means antiderivative derivative. I'm going to write in words of x to Vn, and that is really equal to 1 over n plus first x to Vn plus first, and you add a constant c if you like. So this is, folks, the type of table that's given in your book at page 331. Now, this is one table that you want to remember. It's very much a copy of a table from the section 3.9 on antiderivative, just written in different with a different type of notation. So what I'm saying here is that the page, the table. So be aware, folks, that the table 2 on page 279, section, let me say here clearly, section 3.9, antiderivatives. All right, is the same as table, let's see, 1 on page 331, section, this is in section 4.4, title of this section, indefinite integrals. Oops. Okay, so what I'm just gonna leave it like that, section 4.4. So just be well, you know what? Hang on a second. So let me write that. So let me write that a little more compact. Is table 1 on page 331, section 4.4. Oops, forgot to delete that. All right, section 4.4, which is indefinite integrals. Indefinite integrals, some other stuff as well. All right, so folks, so do remember those are not different. It's just a rewriting of the other, of each other. So when you look back in your notes, do remember these things, because it's very important, and don't be fooled by the different. So you might be thinking, I've seen kids who look at this and they say, oh, that table is different. No, it's not different. So they're thinking it's a new table or something. So it's not different. It's just the same. The one that was in the page in the section on antiderivatives. It's just the same table. It's just written with the integral notation. So that's all there is there. All right, so that's one thing. And what they call here the net change theorem, again, is just a fundamental theorem of calculus. So with that being said, I'm going to do a bunch of problems here to to review these things and show you that actually it is the same. So we're gonna. This is also gonna be a review, folks, for the quiz, because on the quiz you will get a bunch of questions like these. So let's start with number 5 of section. These are all going to be from section 4.4. The integral of, let's see, what do we have? X to the 1.3 plus 7 x to the 2.5. And again, please pause this video if you work at home and try to do this problem on your own. So what does it mean? It means that I want the antiderivative of this guy. To get the antiderivative, what I have to do is to get the antiderivative in pieces, right? So for x to the 1/3, I'm going to get the antiderivative as being 1.3, I'm sorry. 2.3 is 1.3 plus 1, right? And then 1 over 2.3, all right, plus x to the 3.5, and then times 7 over 3.5. All right, so this is going to be the antiderivative, folks, of the function that we're talking about. And then if you want to be fancy, again, I said you want to put a C. Not so useful for Calc 1, but very useful in Calc 2. All right, and differential equations, maybe some other stuff. So this is the answer to my problem. Again, we're doing antiderivatives. We're not doing anything new. So that's the answer to question 5. Let's do question. So the next question is question 6. Now, we have not done something quite like question 6. Even though we did antiderivatives, this is going to be probably the first example when you see this kind of thing. We did square roots and things like that, but not exactly this one here. So we're talking about the antiderivative of the 4th root of x to the 5th dx. What is this thing, folks? Well, here we go. So first of all, before you do this problem, again, as we did with all the antiderivatives, what you want to do, you want to rewrite the 4th root of x to the 5th. You want to rewrite that as x to the 5/4 dx. And then we are going to integrate that as follows. So remember, folks, why 5/4? The index of a root here is always going to be the denominator. The power, the exponent here of the power is always going to be the numerator. So the antiderivative of this guy is following the usual rule where you are going to increase the exponent by 1. So that's going to be 5/4 plus 1, and then 1 over 5/4 plus 1. And all you have to do is to calculate that. So it's very easy to calculate. 5/4 plus 1 is 9/4. So when you write the final answer is 4/9 x to the 9/4. All right, and then plus c plus the constant c at the end. So this is going to be your final result for this particular problem. If you want to write it, and probably in the book they might write something like this: 4/9. Now when you have 9/4 here, so that's the 4th root of x to the 9 plus c. I don't know if that makes a difference. I'm not gonna go that detailed about these fractional exponents. My hope is that you are able to handle those in practice, folks. This is where the problem ends, by the way. So this could be a good answer, and this could be a good answer. So it's up to you which one you choose. So my opinion is that my experience is that these fractional exponents and things like that, they're useful in practice. Maybe the 1/2, maybe the 1/3, but not more than that. So this problem here is already an artificial problem. In practice, you will not run into questions with that kind of tricky exponent. All right. So that's one thing, and then there's a bunch of other questions in the same along the same line of ideas. We did one yesterday with a product. I'm gonna do another one today, so that will be number 10 of section 4.4. And that means the integral from of square root of t squared plus 3t plus 2 dt. So this is going to be equal to, folks, when you see a product like this, remember for integrals, there's no such a thing as a quotient rule or a product rule. In fact, there is something similar to a product rule, something that you will learn in calculus too, and that's called integration by parts. But we don't do that here. So in order to give ourselves some hope to solve this problem, and maybe even in calculus too, this is so that is a tool that you apply if you run out of options, really, folks. So most of the time, what you want to do, you want to split the product. You want to write out the product here carefully, and you want to finish up this thing to the point where you don't have to deal with products anymore. So what I'm going to do, I'm going to keep in mind that this the square root of t is the same as t to the 1/2. And when I multiply t to the 1/2 times t squared, so I multiply term by term, I distribute here, right? T to the 1/2 times t squared is t to the 1/2 plus 2, which is t to the 5/2. All right, the next thing is t to the 1/2 times 3t, which becomes 3t to the 1/2 plus t is 3/2. And then finally 2t to the 1/2. All right, dt. All right, folks, so now this is a problem written nicely without any sort of problems. We don't have any products anymore, and we just calculate the antiderivative. So t to the 5/2 is going to go up by 1 when we calculate the antiderivative. So remember these symbols, integral and dt, that in your head, that should scream antiderivative, right? So it's t to the 7, I'm sorry, 5/2 plus 1, which is 7/2 times 2 over 7, right? 1 over 7/2, which is 2 over 7. It's as much as they're pretty much flipping over the exponent, plus t to the 3/2 plus 1 is t to the 5/2. And then there's 3 times 2 over 5, so which will be 6/5. All right, plus 2 times t to the 1/2, and that's going to be t to the 3/2. I'm sorry, let's write t 3/2 here properly. 1/2 plus 1 times 2 times 2/3, which is 4/3, plus a constant c. So this is, folks, this is the integral, the result of the integration. So this is the antiderivative. Again, very much you saw this type of problem on the previous in the previous lesson in 3.9. We just did not say integral dt, but rather we said antiderivative, which is, as I said, the exact same thing. All right, so we covered half of the material that I wanted to. There's this one here with a quotient. Let's do this one here with a quotient. So let's see if we so it's a good idea to do something like this as well. Let's do number 11 as well. Since we started here with a product, let's do a quotient as well. So I wasn't planning to do this one, but now I'm thinking that might be a good idea. So there we go, folks. So the integral of 1 plus square root of x plus x divided by square root of x. So I like to put these problems. I like to put these problems in class as practice questions, because this is really the type of question that triggers a lot of thinking, a lot of brainstorming from students. And now in a recording is not a good idea to to leave dead times and dead timing, and kind of let the tape roll while you folks try the question. So I'm going to do the problem myself. But what I want you to do, and again, if you happen to watch this video at home, or you take notes and you look over your notes, do look at this particular problem and think, how was I going to do this problem if I were in an exam situation? And that brainstorming, even if you fail to do the problem, that brainstorming is very important, because it tells you, even if you don't do anything and you just look at the problems and think, oh, how am I going to approach this problem? Can I do something about it? That thinking, even if you entirely fail to find an answer to that, that will put you in position to be prepared for the next step in the discovery, where guided discovery, where I'm telling you what the secret is. So the secret over here is, folks, and again, stop the video and you can pause. You can think yourself what that would be. The secret is to eliminate this denominator. For instance, that's one of the ways to deal with this, and write it as a product with negative exponents maybe, but that will pretty much simplify quickly. So let's see. Again, we don't solve the integral. We just rewrite this thing first. Then we calculate the antiderivative. So first of all, my integral is 1 plus x to the 1/2 over here plus x times, and instead of saying divided by square root of x, I'm going to say times x to the negative 1/2. And that is the key secret to this problem. And you will see now similarity between this problem and the previous one, where we had the exact same thing. It's just that there we had positive exponents. So this is going to be equal to the antiderivative of x to the negative 1/2 plus x to the 1/2 times x to the 1/2 is negative 1/2 is 1, plus x times x to the negative 1/2 is x to the 1/2 dx. All right, folks. So we multiplied here again 1 times x to the negative 1/2, no doubt there. X to the 1/2 times x to the negative 1/2 is x to the 0 or 1. That's why 1. X to the first times x to the 1/2 is x to the 1 minus 1/2, which is x to the 1/2. So we are ready to do the antiderivative, which is a piece of cake this time around. X to the negative 1/2 plus 1 is x to the 1/2. And I multiply here by 2 because it's, flip over the 1/2. Plus 1, which turns into x, the antiderivative, plus x to the 1/2, which turns into x to the 3/2. And then over here times 2/3. And then plus a constant c. All right. So this is the answer to our problem. This is the answer to our problem. Now this being said, the problem that you see here, folks, could have been done by simply splitting up this fraction in 1 over square root of x, square root of x over square root of x, and x over square root of x. So that's true. But generally, you might have a harder time seeing that while this distribution of the product is always more or less straightforward, or at least from my experience, students find that a straightforward calculation, so it's not terribly difficult. That being said, I am going to do a next problem here. So these are problems again from the assignment. And right now I'm going to do something that is different. So I said that I will move to a slightly different topic and I'll do definite integrals where we apply that net change theorem. Again, this is just a repetition of the section in 4.3, where number 19 here, folks, from 4.4 is this integral from -2 to 3 of x squared minus 3 dx. All right, and by the fundamental theorem of calculus or the net change theorem, what you have to do is to take a look at this function, x squared minus 3. So before you do any work here, take a look at this, find an antiderivative of x squared minus 3, which is, we can say quickly here, capital F of x equal to 1/3 x cubed minus 3x, one antiderivative, right? And then say here, well, the answer is capital F of 3 minus capital F of -2. So that will be the way to approach this problem. And you can just plug in the numbers here, and I'm going to do quickly here. So when you plug in 3, you get 3 cubed over 3, which is 9, minus 3 times 3, which is again 9. So that's going to be 0. F of 3 turns out to be 0 minus f of -2. F of -2 will be 1/3 times -2 cubed, which is -8/3 minus 3 times -2, which is -6. So when we put these all together, so this is going to be 8/3 plus 6, and that's going to be some number. If you want, it's going to be 18 plus 8, 20. 18 plus 8, 26 over 3 if you want. All right, so this is the answer for this particular integral. Now, the reason why I did it this way is so that you remember exactly the steps that were outlined in section 4.3. However, this problem, the way they want us to write here in this section is slightly different. So I'm going to redo this problem. And I'm going to write the integral, -2, 3, x squared minus 3 dx. And the way they expect us to do this integral, and this is kind of the mechanical way to do the problem, if you want the algorithmic way or so, in the book they say drop the bounds here. Why would they say drop the bounds? Well, if you drop the bounds and you write integral of x squared minus 3 dx, what you're really doing here, you're calculating an antiderivative. And then it says, calculate that, evaluate that from x equals, 3 should be, 1 second, folks. Okay, so come on. This is -2 here, and this is 3 over here. So I got my pen stuck out there when I was trying to change from eraser to pen. All right, so folks, this is what they say to do in the book. So basically do this thing, and then at the end do that thing. That's exactly the antiderivative here. So that's just another way of saying find the antiderivative. So if you feel more confident doing this way, I don't really care. Just remember that some people are picky. So your instructor in calculus 2 may be picky and may want you to do the problem exactly this way. So that's why you wanna learn this formalism as well. So anyway, this is the antiderivative, and we just calculated that, and we said is 1/3 x cubed minus 3x. So the antiderivative is that here, the one that's circled. And then we say we evaluate that from x equals -2 to x equals 3, which means that we're just going to substitute 3 and -2 in the formula. So we have 1/3 times 3 cubed minus 3 times 3. And we just figured earlier that that was 0 and minus. And then we have 1/3 times, let me increase this size here. I it's more. Okay. All right, there we go. So there's more room here. 1/3 times negative 2 cubed minus 3 times negative, okay, so negative, you know what? I think I made a mistake with the signs. Yep, I made a mistake with the signs there, folks. So let me see. So minus, okay, so then negative 2. All right, so there we go. So now I found a mistake. So my calculation was incorrect here. So I should have done this. I should have done this, folks. Negative 8/3. Okay, so that would have been negative 8/3 plus 6. 6 minus 8/3 is 18. Minus 8 would be 10/3. So so the answer over here will be negative 10/3. And we can see here again, so I see that's a good thing that I did it algorithmically this way because I didn't pay attention there. So I apologize for that mistake. So over here we have 1/3 times negative 2 cubed is negative 8/3, and plus 6 we just calculated earlier. That's 10/3, and the answer is 0 minus 10/3, and that's going to end up being negative 10/3. There we go. Got the correct answer. All right, folks. So the correct answer is it's going to be minus here, and that's going to end up being that. There we go. So 10/3, negative 10/3 is the correct answer. Just get the pen here. There we go. So so folks, from this point on, we are going to do definite integrals by using this procedure here, which again, it's the exact same way as doing the fundamental theorem of calculus, but we're using this symbolistic approach with symbols. And I'm going to move on, and I'm going to say, let's do, we're going to do a couple more problems in the amount of time that's left to us here. So the first thing that I'm going to do is number 23. All right, folks, so number 23 over here from section 4.4. Please do the other problems all the way to 23. 23 is slightly different. And what does 23 say, folks? So it says the integral from 0 to 2, 2x minus 3 times 4x squared plus 1 dx. Wonderful problem. Now here we go. So let's do what we said earlier. So we're going to write, first of all, we're going to write this without bounds, right? So we're calculating the antiderivative of 2x minus 3 times 4x squared plus 1 dx. And that is equal to, so the antiderivative is, so now we cannot calculate the antiderivative just like that. We said that we want to distribute this thing and, write powers of x. So what we're going to do, we're going to do a little bit of prep work for this thing. So we're going to write that as 8x cubed, right, 2x times 4x squared, 2x times 1 is plus 2x, minus 3 times 4x squared is minus 12x squared, minus 3 dx. And that's the antiderivative that we want to evaluate. Now, I'm not going to write yet the bounds 0 to 2 because I don't want to make the notation too complex here. But this antiderivative is now easy to evaluate. Remember to keep parentheses. Don't make the mistake that I did earlier in the first problem here, where I forgot to put the parentheses and then things got messed up because I forgot to keep track of a sign. So a times x third, the antiderivative of that will be will be a times 1/4 x to the 4, right? So will be 2 because 8 over 4 is 2 times x to the 4 plus 2/3. 2x. The antiderivative of that is 2 times 1/2 x squared, which is just x squared, minus. For 12x squared, the antiderivative is 12 times 1/3 x cubed, so which is going to be minus 4x cubed. then minus 3x, the antiderivative of 3. And we are going to say, well, this is the antiderivative. Now we evaluate that from 0 to 2. And here's a quick observation. Folks, when you have 0 to be evaluated and you have things like that, you get 0, 0, 0, 0, so that's 0. So you don't have to worry much about that. So all you have to do is to evaluate at 2 and make sure you keep the correct sign. So it's 2 times 2 to the 4 plus 2 squared minus 4 times 2 cubed minus 3 times 2. And then we say minus, and then we have 0, right? Because you plug in 0, minus 0. You don't have to write that down if you don't want to. And the answer here will be 2 times 2 to the 4 is 32 plus 4 minus 32 apparently, yep, minus 6. So this is going to end up being, these two will cancel out, 4 minus 6, negative 2. There we go. So that is the answer to this particular problem. And one more, and we'll be done. This, as I said, sometimes we need to involve a little bit of trigonometry. So what we are going to do here is the following. Number 25 of section 4.4. There's going to be a lot, folks. There's going to be a lot more trigonometry in calculus 2. So bear with me here because it's important to do this type of problems. Integral 0 to 0 pi 4 sine theta minus 3 cosine theta d theta. How do we calculate this? Well, here's how we calculate. Again, drop the bounds for the moment. At the end, when you find the antiderivative, put the bounds back. Right? So 4 sine theta minus 3 cosine theta. So that is an antiderivative now. Calculate the antiderivative. So basically, we're getting rid of these symbols we say formally, informally. So we calculate the antiderivative, which means 4 sine theta, the antiderivative is 4 negative 4 cosine theta, and minus 3 cosine theta, the antiderivative of that is minus 3 sine theta. And all of these parentheses, folks, that's going to be from 0 and then over here pi. So we're going to substitute pi and 0 in the formula, and we get negative 4 cosine pi minus 3 sine pi minus negative 4 cosine 0 minus 3 sine 0. That's going to end up being cosine pi. Again, that's one thing you need to remember. Negative 1. So negative 4 times negative 1 is 4. Minus 3 sine pi, 0. So that's 0, that's negative 1. Minus 4 cosine 0. Minus, and over here we have minus 4 cosine 0 is negative 4 because cosine 0 is 1. And minus 3 sine 0 is 0. So minus negative 4. So 4 minus negative 4 is 4 plus 4 or 8. That is going to be the final answer. And we are done with today's lesson. If you folks have any questions, again, we did a lot of practice problems here. This is the type of questions that you will see on tests. So I want you to really pay attention to this section, and these problems are really good practice problems for you. I'm going to, again, to send out some further practice problems for the quiz. And let me just stop sharing here this thing, folks.